Hello everyone, and welcome to Lecture 15 of 124103 Biophysical Principles. In this lecture, we will learn about temperature. At the end of this lecture, you should be able to state the SI unit for temperature, convert between Celsius and Kelvin, and calculate linear and volume expansions due to the temperature change. What is temperature? We perceive temperature as how hot or cold an object feels. But if we look deeper inside to see what is happening to the molecules that make up the material, we will find an association between temperature and how fast the molecules are moving. If you watched the pre-lecture video, you would have learned that the faster the molecules in the material are moving, the higher the temperature of the material and the hotter the material feels. So for example, in this material, molecules closer to the flame move faster compared to the molecules that are farther away. How do we measure temperature? It is very common that temperature is measured in degrees Celsius. But the SI unit for temperature is the Kelvin, abbreviated as capital K. When converting degrees Celsius to Kelvin, we simply add 273.15 or just 273 to the Celsius temperature. Try converting degrees Celsius to Kelvin and vice versa in these examples. In the last one, you will have to convert temperature difference. I will give you a few minutes to do the conversions, or you can pause the video and restart after doing the conversions. Okay, let's answer the first question. Water freezes at 0 degrees Celsius. We want to convert 0 degrees Celsius to Kelvin. As we've seen in this equation here, to convert Celsius to Kelvin, we simply add 273 to the Celsius reading. So 0 degrees Celsius is equal to 273 Kelvin. In the second example, we want to convert 63 Kelvin to degrees Celsius. In this case, instead of adding 273, we subtract 273, and that will give us negative 210 degrees Celsius. In the next question, we are being asked to convert 46 degrees Celsius and 60 degrees Celsius to Kelvin. So that will be 46 degrees Celsius plus 273 is equal to 319 Kelvin, and 60 degrees Celsius plus 273 is equal to 333 Kelvin. And in the last question, we are being asked to convert a temperature difference of 14 degrees Celsius to Kelvin. Now, a common mistake is to convert 14 degrees Celsius to Kelvin by adding 273, giving an answer of 287 Kelvin. However, this solution is wrong because 14 degrees Celsius is the temperature difference that was obtained by subtracting 46 degrees Celsius from 60 degrees Celsius. Therefore, if you want to get the temperature difference in Kelvin, we need to subtract 319 Kelvin from 333 Kelvin. If we did that, we will get 333 Kelvin minus 319 Kelvin is equal to 14 Kelvin. So we can see here that when taking the temperature difference in Kelvin is also equal to the temperature difference in Celsius. Therefore, you can just directly substitute the unit degrees Celsius with Kelvin, and that should give you the correct temperature difference. To see this in more detail, let's try to get the temperature difference by subtracting these two temperatures with the Celsius being converted to Kelvin. So that will be 60 degrees Celsius plus 273. Okay. So that's for this bit here, minus 46 degrees Celsius plus 273, and that's for this bit here. If we expanded this equation, you have 60 degrees Celsius plus 273 minus 46 degrees Celsius, and then this negative sign here will multiply with that positive sign there. So you will have a negative 273. And notice how this 273 here will cancel with this 273 there. Therefore, we are left with 60 degrees Celsius minus 46 degrees Celsius, which is equal to 14 degrees Celsius. And therefore, we can see that when we're converting temperature difference, the temperature difference in degrees Celsius is equal to the temperature difference in Kelvin. We just need to change units from degrees Celsius to Kelvin or Kelvin to degrees Celsius. Now, as mentioned in the earlier slide, the higher the temperature of a material is, the faster the molecules in that material move. And the faster the molecules move, the farther they move apart. Therefore, in most substances expand when they are heated and contract when they are cooled. This expansion and contraction is the reason why there are some gaps on roadways or sidewalks. In this figure, for example, these gaps here are called expansion gaps that will accommodate the expansion of this road in warmer weathers. This is an example of what could happen when a railroad track expands and there are no gaps to accommodate the expansion. Notice how the railroad tracks buckled and bent when the metals expanded. Thermal expansion of the metal lid will also make it easier to open a bottle after running the lid through hot water. Thermal expansion is also behind the operation of a thermometer. A thermometer is a device that is used to measure the temperature of a system. This, for example, is an alcohol in glass thermometer. The liquid inside the thermometer, which is alcohol, or in some thermometers it's mercury, the volume of the liquid inside the thermometer increases as the temperature increases, and the scale gives a convenient way of reading the corresponding temperature. This thermostat shown in this figure gives an example of how the thermal expansion of a solid's dimension is able to tell us the temperature reading. This thermostat consists of two kinds of metals, brass and steel, which expand at different rates when heated. As the metals expand, there is a counter here which tells us the temperature scale of a reading. How do we quantify the thermal expansion of an object when it's heated? If we assume that an object has an initial length L0 at the initial temperature T0, and if the object's length increases by delta L when the temperature changes by delta T, then we can write an equation that relates the change in length to the change in temperature. In this equation, the Greek symbol alpha is called the coefficient of linear expansion. The coefficient of linear expansion has a unit of inverse Kelvin, or Kelvin to the -1. Alpha, the coefficient of linear expansion, is a property of the material. Different materials have different coefficients of linear expansions. For a volume, the change in volume due to the change in temperature is given by this equation. Here, the Greek symbol beta is called the coefficient of volume expansion. Again, beta is a property of the material, and both alpha and beta determine how much something expands. So the higher the value of alpha and beta, the more the object expands when it's heated. Let's look at this example on thermal expansion. I will once again give you a few minutes to try and solve this example, and you can pause the video and restart when you're done. As with any worded problem, it is useful to write down what is given. So let's write down what's given in the problem. We're given the initial temperature, which I write as T sub 0, and that's equal to 30 degrees Celsius. We are given the final temperature, which I'll write as T sub F, T final, is equal to 212 degrees Celsius. We are given the initial volume, V0. To be consistent with the equation on volume expansion, I'll use V0 to indicate the initial volume, and that is 1 times 10 to the -4 cubic meters. We are given the coefficient of volume expansion beta, which is 2.2 times 10 to the -4 Kelvin to the -1. What we are being asked to find is the volume of the compound after being heated. That means we need to find the final volume. We know that the change in volume delta V is defined as the final volume minus the initial volume. Therefore, if we want to find the final volume, given the initial volume, we need to solve for the change in volume delta V. And we can solve for the change in the volume delta V using the equation on volume expansion. Delta V is equal to beta, coefficient of volume expansion, multiplied with the initial volume multiplied with the change in temperature. Note that the change in temperature, delta T, is equal to the final temperature minus the initial temperature. So we can write down this equation on the change in volume as beta V0 multiplied with the final temperature minus the initial temperature. We are given the values for beta, V0, T final, and T0. So we can write down here, beta is 2.2 times 10 to the -4 Kelvin to the minus 1. V0 is 1 times 10 to the minus 4 cubic meters. Okay. For the temperatures, note that we are given temperatures in degrees Celsius, but beta, the coefficient of volume expansion, has a unit of Kelvin to the minus 1. This means that our temperature value should also be in Kelvin so that our units are consistent. But recall that earlier we said that when we are getting the change in temperature, so if it's the change in temperature that we are getting, the temperature in degrees Celsius will be equal to the temperature in Kelvin if we are talking about the change in temperature. So I will just go ahead and substitute the temperature values in Celsius. That's 212 for the final temperature minus 30 for the initial temperature. But since we are getting the change in temperature, I will write down the unit for the change in temperature in Kelvin. Because again, when we're talking about change in temperature, the change in temperature in Kelvin is equal to the change in temperature in degrees Celsius. Okay. Note now that our unit for temperature is consistent in this equation. Both of them are given in Kelvin. Okay, so if we plug in these numbers in a calculator, we can find the value for the change in volume as 4.004 times 10 to the minus 6 cubic meters. I will not round the answer at this point, and I'll just do the rounding at the end. Okay, once we know the change in volume, or delta V, we know that delta V is equal to the final volume minus the initial volume. And if we rearrange this equation to make V final the subject, then the final volume will be delta V, the change in volume, plus V0, the initial volume. Okay, so the final volume will now be 4.004 times 10 to the minus 6 cubic meters plus 1 times 10 to the minus 4 cubic meters, and that is equal to 1.04 times 10 to the minus 4 cubic meters. We've been learning that objects expand when heated and contract when cooled. But watch this video and see what happens when water is frozen. Did you see the unusual behavior of water? What happened when the water became frozen? Did it expand or did it contract? Let's look at this figure here, this graph here, showing how the volume of water changes as the temperature changes. So the y-axis here tells us the volume of water, and the x-axis here tells us the temperature of the water. So as the temperature of the water decreases, as expected, the volume of water decreases as well because the molecules move slower. But if we magnify this region of the graph here near the freezing point of water, which is 0 degrees Celsius, we can see that the volume of water decreases only up to a certain temperature, and that specific temperature is 4 degrees Celsius. As water is cooled further below 4 degrees Celsius, we can see that the volume of water starts to increase, and as water undergoes phase change and becomes frozen, we see this dramatic increase in volume of water. The increase in volume is significant enough that it caused the bottle to break. So what's happening here? Below 4 degrees Celsius, as the water temperature goes below 4 degrees Celsius, ice crystals begin to form. And so water becomes bloated with ice crystals, and that causes the volume to expand. The expanding volume causes ice to become less dense. Recall that density is equal to mass over volume. So as volume increases, density decreases, and the water below 4 degrees Celsius becomes less dense. In fact, at 4 degrees Celsius, when the volume is smallest, that is when the density of water is greatest. And above 4 degrees Celsius, as the volume increases, water again expands and becomes less dense. This unusual behavior of water is actually very important for the survival of life underwater, especially during freezing temperatures. It ensures that the bottom of a frozen pond is always at 4 degrees Celsius. Because at 4 degrees Celsius, water is densest, and so it sinks to the bottom, and at the surface, the temperature is 0 degrees Celsius. Okay, so that ends our lecture for today. Next time, we will learn about heat.